In this video, we will be designing XOR gate and XNOR gate using NMOS pass transistors. First, let us design XOR gate. Here is a simple circuit schematic. This remains the same for AND, NAND, OR, XOR, XNOR, whatever gate it is. For all basic gates, the circuit schematic remains the same. We have to just modify this input and as well as gate terminal variables. In order to do that, first we should write the truth table. In the truth table, we will have two variables A and B. So we'll have four combinations of 0, 0, 0, 1, 1, 0 and 1, 1. In the column B, initially we have to write all zeros and ones. Now, second step, you have to choose the column B. Wherever you find 0, replace everything with B bar. Wherever you find 1, replace it with B. In the column A, we have to do the same. Wherever you find 0, replace with A bar. Wherever you find 1, replace with A. This is the second step. Then, we have to write the output. This output remains the same output of a normal XOR gate. When we have two inputs, both are different, that is 0, 1, 1, 0. For these two combinations alone, the output will be 1. That is why we call XOR gate as inequality detectors. For the other two combinations of 0, 0 and 1, 1, we should have the output 0 and 0. So, right now we have converted all zeros and ones to B bar, A and so on. We'll try to club these inputs together. For that, we are considering the first two rows where in the column B, we find similar variables of B bar and B bar in both the columns. Let us check what is the corresponding output. It is 0 and 1. There is a difference. So anyhow, you have to consider A also. Now let us compare A and F. If it is A bar, it is 0. If it is A, it is 1. What does it mean? Whatever is in A, it is just been transferred. Now our assumption is 1. What are the values that you had in the truth table previously? 0, 0, 0, 1. So A is assumed to be 1. The same values here. A is assumed to be 0 in this location. The same 0 is here. What do we understand from this? Whenever a control signal B bar appears, whatever is in A should be as such transferred to the output F. So, jump back to the diagram. The control signal should be B bar. Whatever is in A should be available at the output whenever we have the control signal B bar. This is what our study is. Therefore, we are assigning A as the input variable so that when the control signal is enabled, whatever is in A will be passed to the output. So, now we have to consider the next two conditions. In next two conditions also, the value is again B and in the fourth row also it is B. Compare the output. It is 1 and 0. It is varying. Therefore, you have to compare this output with the variables in the column A. When you compare, actually A should be 1, but it is 0. A bar should be 0, instead it is 1. What does it mean? It is just the inverted values of A that is present in the output right now. So, whenever you have the control signal B, we need inverted values of A to be present at the output terminal. Therefore, your control signal could be B and the input should be A bar. So, when you have the control signal B enabled, obviously whatever is in A bar will be passed to the output. So with these assumptions, let us start deriving the expression for this circuit schematic. So F should be equal to A into B bar plus A bar into B. This is the expression, which is nothing but A B bar plus A bar B. This is the expression of a simple XOR gate. We directly derived it. Next is a design of XNOR gate. Here It is a simple circuit schematic. Again, it is going to be the same for all 6 gates as we have told already. But this gate terminal values and as well as this input terminal variables, it is all going to vary. In order to do that, the first step is to write the truth table with two variables A and B and as well as the output F. So we'll have 0, 0, 0, 1, 1, 0, 1 and 1. So now what we do in the second step, we have to choose the column B. Wherever we find 0, replace with B bar. Wherever we find 1, replace with B. In the second column, that is A, wherever we find 0, replace with A bar. Wherever we find 1, replace with A. Whenever the input combinations are similar, the output will be 1. For 0, 0 combination, output is 1. 1, 1 combination, output is 1. For the other two combination, it will be 0. It is exactly opposite of what XOR gate is. Now, consider the first two set of values, that is two rows of your truth table. It is B bar and B bar in the B column. What is the output? It is 1 and 0. Now, compare this F with A. It is A bar. A bar means actually it should be 0, but the output is 1. A. Actually, it should be 1, but the output is 0. That means whatever is in A is inverted at the output. Therefore, for the first combination, the control signal is B bar and you have to invert A. Therefore, whenever the control signal is B bar is enabled, inverted value of A will be passed at its output. For the next set of combination, both are B. Look into the output. If it is A bar, it should be 0. Yes, correct. If it is A, it should be 1. Yes, it is correct. Therefore, whenever the control signal B appears, whatever is in A is transferred to F. Therefore, control signal is B, it is A. So, when we write the expression together, it is A bar into B bar plus A into B. So, A bar B plus A B, which is the expression of an XNOR gate. Therefore, just by changing these values at gate and input terminals for the same figure, we right now got an XNOR gate expression. I hope the explanation for XOR gate and XNOR gate both are clear now. Thanks for watching.